Okay, this video goes over the hypothesis testing homework solutions. In problem 1, we have data on how much a family spends per week on their grocery bill. And your job is to develop a confidence interval and then do a hypothesis test to see if the difference is statistically different than $100. So I did a descriptive stats and got some information I'm going to need, and I used this confidence level number to generate my upper and lower from the mean. So the mean is 101, and so I can say that I'm 95% sure that the mean is between $99.47 and $103.56. It's not quite the same definition, but it's close enough for what we're doing. And you can see that 100 is in that. So I can't say, since 100 is within that, that's important. Because on part B, when we did the hypothesis test, the null hypothesis that the mean equals 100, we try to prove that it's different. With the alternative, we're going to set alpha equal to 0.05. Our t-value, we're going to calculate that by taking the mean minus 100, it's in my numerator, divided by the standard deviation, divided by the square root of how much data I've got. To get this, and then I can calculate a p-value by taking the t dot dist, and I'm going to use the two-tail because it's a two-tailed test because of my alternative hypothesis is a not equal to dot 2t. And I put in my t-value. My degrees of freedom are the count minus 1. And I get a p-value of 0.14, which is greater than 0.05, so fail to reject the null hypothesis. And so you can see that A and B are giving us the same answer. In B, we don't have evidence that the average amount is different than 100. And you can see that the confidence interval includes 100. So I don't have any confidence that 100 is outside of my confidence. So it's the same math in one sense, is that when you do a confidence interval, you're doing the same thing as hypothesis testing, provided you use the same type of alpha. Problem 2 is a before and after question. A company president is deciding whether to adopt a lunchtime exercise program. We have a before and after. And it's the same group of people, so we're going to use a paired t-test. So if I go under data analysis, do a t-test paired, in the variable 1 range, I'm going to grab, let's see, what is it asking? Medical expenses. So I'm going to grab the higher one. So that would be the before, and then variable 2 is the after. I have labels, and I'm going to go ahead and the output range be here. So step 1, I'm looking at the differences, average differences, the average difference equals 0, and I'm going to try to prove the average difference is less than 0 or greater than 0 if I do the before first. Step 3, alpha, choose 0.05. Step 4, what's my t-stat? It's equal to this. Calculate a p-value. It's already given to us. It's a one-tailed test. So it's this. Statistical conclusion, p-value is greater than alpha, less than alpha. We're going to reject the null hypothesis, and the practical conclusion is that expenses went down. We have evidence that the medical expenses statistically went down. Problem 3 is looking at two types of colors of softball and the number of errors. If I look at the errors with a yellow golf ball, which was used in more games than the white, that's fine. Sometimes we don't have the balanced data. We have a lot more errors with the white. The question is it statistically different? The question is, can we infer that fewer errors occur when the yellow ball is used? So yes, it's less, but we don't have as much data, and we have one huge number there. So the question is this statistically smaller than this? Well, we've got to do two things. The first, we've got to do a t-test, H0, where the average for the white is assumed to be the average of the yellow. These are errors. And the alternative is that we're trying to prove if the average white is greater than the average yellow. Set alpha 0.05, or let's do a t-test. The question is, which t-test do we do? Equal variances or unequal? Well, we don't know, so let's go and test the variances. I'm going to start another one over here. And let's go and calculate the variance. The variance is more, but is it statistically more? 8-0. Usually you use a ratio, so were you looking at the ratio of the variance of the white over the variance of the yellow, and we're assuming that it's 1. If they were the same, then the ratio would be 1, and we're going to try to prove that the variance of the white over the variance of the yellow is greater than 1. Set alpha, let's do 0.05 again, 4, let's calculate an f-stat. And now I can go under data analysis and do my f-stat, 2 sample variances. I'm going to grab the higher one first. Grab the second one, the smaller one second, the white, in terms of variance. Labels, and I'm going to go ahead and put the data there. So my f-stat is this, 4, p-value is this, and that's a really big p-value, so since the p-value is greater than alpha, we fail to reject the null hypothesis. And the step 7, no difference in variances. We can assume that they're the same, so now we can go back to doing a t-test, assuming equal variances. I'm going to grab the larger one first. Grab the smaller one second. Labels. I'm going to go ahead and put the data, the output here. Now my t-test is this, and then I calculate a p-value, which for a one-tailed test is that, and it is smaller since the p-value is less than alpha. We can reject the null hypothesis. And yes, we can say that yellow softballs have fewer errors. When you play games with yellow softballs, you have fewer errors. It's not a lot of data. It's only a handful of games. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9 games versus 8 games. So only 17 games. But even with that, these are large enough that we have statistical evidence that they are give different results. Problem 4 was trying to determine if classifications, freshmen, sophomore, juniors, impact attitudes on corporations. So do they favor corporations, or are they neutral, or they don't favor? This is a count. These are counts. Think about a survey where we ask someone, we go out on campus and we ask them, what's your classification? They would say freshman. And then we say, do you favor corporations? Yes, or favor, neutral, or unfavorable. And they would give us one of those. That would be one data point. So we did this a whole bunch of times. We did it 800 times. And from that, we want to know if the classification is independent of their opinion. And we can use the row total times the column total divided by the overall total to calculate an expected number if these were independent. This is what we really got. This is what we would expect to get if they were independent. Then we can calculate the observed, or expected minus the observed squared over expected, which we use for the chi-squared test. And then we total all this to get this number. We assume that they're independent. We try to prove otherwise. Set an alpha. Chi-squared we calculated. We use the chi-test stat. Remember, when you do this, always grab what really happened first. You'll get it wrong if you grab the expected first. Got a very, very small p-value, which we can reject in all hypothesis. And yes, they are related. We don't say one causes the other. That's a different test, but at least we can go down that path to say they're related. The last problem is an ANOVA, where we're looking at a product against 2 other products. And the measurement in this case are the number of scrubs in the thousands before the paint wears out. So this is how many scrubs it takes. We ran a total of 15 different trials. Keep in mind that this trial is not related. These numbers are not related to these or these at all. So the row doesn't mean anything. It's just that we ran 5 trials with the one coat, 5 trials with product A, and 5 trials with product B. Since we had more than 2, let's use ANOVA instead of a t-test. Our null hypothesis is that there's no difference, and then the alternative is that at least one is different. We use an alpha of this. We did our ANOVA, which comes from our ANOVA table. We calculate a p-value. P-value is not real small, but it is small enough to say that yes, there is a difference. So after that, we calculated the averages and a confidence level from our descriptive stats, and then from that I built a graph. And you can see that the one coat overlaps with A, but it does not overlap with B. So the conclusion is that one coat is better than B, but we can't say it's better than A. Thanks.